Hello, welcome to Chapter 3 of Intro to Psychology. In this video, I'll be talking about the different ways to study the brain. The brain is a very difficult organ to study, primarily because, from a historical perspective, it was difficult to gain any information about how the brain works without removing it from a person's skull and killing the owner. Throughout history, there have been several individuals who have learned lots of useful information about the brain by kind of taking advantage of the situation that many people found themselves in after suffering some kind of brain damage or some kind of accident. For example, Paul Broca, a French neurologist, conducted autopsies on individuals who had lost the ability to speak. And so he compared the brains of individuals who had lost the ability to speak to the brains of individuals who had intact speech, and notice a particular difference. Right here, in the left inferior frontal lobe, he noticed a region that was constantly or most commonly damaged in people who had impaired speech production. And so now we know that that area, because of that difference in anatomy, is related to our basic speech functions. And now there's a disease called Broca's aphasia. In Broca's aphasia, people have difficulty producing speech on their own and often have other language difficulties and almost always have some kind of lesion or some kind of damage to that area of the brain. Another famous example is that of Phineas Gage. Phineas Gage was an American railroad worker who was largely remembered for his improbable survival of a railroad accident in which a large iron rod, as you can see in that image on the right, there was an explosion that sent the rod right up through the bottom of his jaw, all the way through his left frontal lobe. He miraculously survived the accident, and his family and friends noticed some very interesting changes in his behavior and personality, comparing before the accident to after the accident. Before the accident, he was quiet and industrious, a good worker. And then after the accident, when he eventually recovered it and came back to work, he was combative, he was argumentative, he couldn't hold a job, he couldn't get his work done. He was almost like a completely different person. And his accident and subsequent recovery provided early evidence that personality is in part controlled by the activity of the frontal lobe. Luckily, advances in technology in the late 20th century have introduced new ways for us to study the brain and study the brain without relying on people having accidents or waiting until people have passed away. There are some diseases where that's still true, but luckily we have two main types of brain imaging that can give us lots of valuable information about the brain. So the first is structural neuroimaging, which allows us to identify changes in the structure of brain and brain regions. And then there is functional neuroimaging, which allows us to identify changes in the activity of certain regions of the brain while performing a particular task. So for example, if you have someone who suffers a stroke and they have bleeding on their brain, they might go into the hospital and get some kind of structural neuroimaging so that doctors can locate where in the brain, what has been the change in the structure or in the brain regions, where is the bleeding coming from, to better map out what part of the brain has been impacted by the stroke. Whereas if you are doing a research study and you'd like to know what part of the brain is active when you're watching a movie or doing a task like solving a puzzle, then you would use some kind of functional neuroimaging, something where you are recording someone's brain activity over a particular span of time. So to say some more examples, so two examples of structural neuroimaging are CT scans or CAT scans. That's the same thing, as well as magnetic resonance imaging, MRI scans, as you've most likely heard of. The advantages of these two methods are that they both have good spatial resolution. They allow us to see in great detail the different structures and the different details of all the different parts in the brain, as you can kind of see in that image on the right. CAT scans are really just 3D X-rays, and MRI scans use a magnet and a specific radio frequency to pulse images through the brain and really create a really rich image of all the different parts of the brain. The disadvantage of using structural neuroimaging methods like these two is that they have poor or really no temporal resolution. So when I say temporal resolution, I'm talking about time. They don't tell you any information about time. So when you look at a CT scan of someone who's had a stroke, it doesn't tell you exactly when the stroke occurred. It doesn't tell you how long. It just tells you where. So it doesn't answer the when question. It just answers the where question. Two examples of functional neuroimaging methods are fMRI, functional magnetic resonance imaging, and PET scans, so positron emission tomography. And both of these have good spatial resolution as well as good temporal resolution. So they tell you a little bit about the where and as well as the when. So they can tell you when a particular brain region is active during a particular task. fMRIs look at changes in blood oxygen concentration in the brain. So when your brain is involved in doing a demanding task, more blood goes to that region of the brain, and so they use that as a proxy to determine which parts of the brain are more active during a particular task. And then in PET scans, there's a specific chemical, a specific contrast agent that is sent through the brain so that they can similarly get information about the different brain regions that are active during a particular task. One disadvantage of these functional neuroimaging methods is that they're more expensive. They're often uncomfortable. They have limited mobility. That's also true for structural neuroimaging methods. They're not perfect. They don't tell us everything, and I'll also add that they are proxies. They don't tell us, each one of them is using some kind of a proxy of brain activity. We don't know exactly what activity in one area of the brain means for one person, and if it means the same thing for another person. Oftentimes, the studies that use fMRI, for example, are taking averages across a range of individuals, and oftentimes activation during the same task looks very different from one individual to the next. A final example of a functional neuroimaging method is EEG. So EEG is when you might have seen people with this kind of cap on. It has various different forms with these electrodes that are attached directly to the scalp. Those are recording electrical activity that is emitted directly from the scalp, and it provides excellent temporal resolution. It's really, really accurate when it comes to identifying changes that happen over the course of time. So when someone blinks, you immediately see a reaction on the EEG scan. However, it doesn't tell us anything about space, or it doesn't tell us very good information about spatial resolution. So if you look at the diagram below, you can kind of see that there's lots of activation in this kind of frontal region during this particular task. It doesn't tell you exactly where in the brain, like an MRI scan or an fMRI scan might, but it does tell you the kind of global region where that activity is coming from. So here are some quiz questions just to review what we've learned. Which two of the following brain imaging techniques would be best for finding the location of a tumor in the brain? So this one's pretty easy. The keyword is location. So the answers would be CT scans and MRI scans, A and B. So those are two structural neuroimaging methods that allow you to determine the location or the where of changes in the brain. Which two of the following brain imaging techniques would be best for showing the brain regions that are active during a particular task? So the answer here would be C and D, an fMRI scan or a PET scan. We would not say an EEG scan because it doesn't offer as good spatial resolution. So it wouldn't tell you that much about the specific brain regions, particularly subcortical brain regions that are active during a particular task.